Hi, in this tutorial we are going to talk about vectorization and how it can perform efficient computations. But first, what is vectorization? So, vectorization is the process of transforming a scalar operation acting on individual data elements to an operation where a single instruction operates concurrently on multiple data elements. So, in simple words, vectorization means transforming or converting an operation or algorithm from operating on a single value at a time to operating on set of values at one time. Here, as you can see in this example, 2 plus 2 is 4. Here, plus is acting as a scalar operation because it's adding only two values. But in second part, we have two matrices and addition operator is adding four different values at the same time. So this is an example of vectorization. And now let's talk about how it can perform efficient computations. So in programming, it simply replaces our for loop with arrays. And in this conversion, Numpy module help us a lot. And I think that much discussion is enough for vectorization. Let's understand it with examples. So I'm on Colab and this is the outline of this tutorial. First of all, we will see how it can perform efficient matrix operation and then how it can calculate efficiently our functions, and finally we will see the time complexity graph of arrays and for loop. So first of all, let's discuss matrix operations. And in matrix operations, we are going to talk about the dot product specifically. Now, what is dot product? So let's suppose I have two matrices, matrix A and matrix B. In matrix B, we have B1, B2, B3, and in matrix A, we have A1, A2, A3. And taking the transpose of matrix A, we will get a single row with three columns. And now, if you take a dot product of matrix A with matrix B, you are going to get only a single value. So this is how this dot product will look like. You need to multiply A1 with B1, then a plus operator, then A2 with B2, a plus operator, and A3 with B3. So let's implement it in Python. Let's create here two matrices first. So let's import Numpy, and matrix A is going to be np.random.rand integer, and the integers are going to be between 10 and 20, and the size is going to be 10,000 rows and one column. And let's create here our matrix B. The numbers are going to be between 10 and 20, and make sure that you should put here the same size, otherwise the dot product will not work. So 10,000 rows and one column. And in NumPy, we have a function called dot operator, which allow us to calculate the dot product of two matrices. But we need to calculate the efficiency. So let's start our timer. Start is equals to time.time. So we are starting our timer here. And now let's calculate the dot product and see how much time it is taking. Numpy dot dot, and we need to pass our two matrices A and B. But we have a problem here, and that is currently matrix A has 1000 rows and one column, and matrix B has 1000 rows and one column. Both have the same size, but in this example, as you can see, we need to take the transpose of matrix A in order to calculate the dot product. So instead of passing here A directly, we need to write here dot T to take the transpose. We are going to have one row and 10,000 columns in matrix A, and in matrix B, we are going to have 10,000 rows and one column. And after calculating the dot product, we need to stop our timer. So stop time.time. Let's import this time module and let's calculate the difference. Cal time, calculation time, and it's going to be stop minus start we need to multiply the result with 1000 in order to get time in milliseconds. And let's print the result as well as the calculated time. And let's run it. Oops, it's not NumPy, it's NP. Result is going to be a string as well. And yes, the time it took for calculating this result is 0.2 milliseconds, so it's a very small amount of time. Now let's do the same calculation using the loops and see how much time loops are taking for calculating the dot product of two matrices. So let me write here vector product, and now let's see the for loop product. So I need to write here a for loop for I in branch 10,000 and put here result to 0 first, and then result plus equals, we need to multiply each number one by one and then we need to add them. So that's why I'm putting here plus equals first item of matrix A multiplied by the first item of matrix B, and we are going to add this result. We need to start our timer again, time.time, and after calculating the result we need to stop our timer. Let's calculate the time. So copy the line, paste it here, and let's print the result as well as the time, and let's run it. Wow, here as you can see, our vector product took only 0.1 millisecond for calculating the result, but our for loop took 56.0 milliseconds for calculating the same product. So this is how vectorization makes our computations efficient in matrix operations. And now let's apply the same concept on calculating our functions. So let's take an example of maybe activation functions. And in activation functions, we are going to calculate the sigmoid functions, which is the base of deep learning. Again, let's create here another array. And this time I'm going to use the linear spacing function of NumPy to create a linearly spaced array. Linspace, it is going to start from -50, it will go to 50, and how many items? 100,000. And again, calculate sigmoid function using the vector operations, vectorization, sigmoid, and the formula of sigmoid is this, as you can see. And in this case, our x is going to be this array. So let's write this formula as it is. We are going to use the numpy exponent function, numpy.exp, and we need to pass our array with a negative sign. And again, let's start our timer and let's calculate the difference, and let's print calculate time variable. Let's run it. Okay, so it took around 9.2 millisecond, and now let's do the same process using the for loop and see how much time for loops are taking. Start our timer, and we have 100,000 entries, and let's implement our same sigmoid formula. This time, instead of using the numpy exponent function, I'm going to use the Python exponent function, which is math.exp, and it's a scalar function. Pass our negative array, but this time, since it's a scalar operation, so we need to pass one item at a time. So it's going to be array I. And now we need to store all of these elements one by one in another array. So let's create here an empty array which is going to store our results. Numpy.zeros, the default values are going to be 0, And what's going to be the shape? 100,000 columns. And now let's store them. And after calculating this result, let's stop our timer. Let's calculate difference and let's print it. Just paste these two lines. Let's run. And yes, our vectorization process took 6.2 millisecond, while for loop took 52 milliseconds for calculating the sigmoid of an array. And if you increase the size, you will see the difference becomes larger and larger and larger. And that's why we need to calculate here this time complexity graph. So let's see the effect of complexity on the time. So let's define here some sizes. It's going to be a list. Let's go with 100, then 1000, million. I think these sizes are enough. And let's iterate on each size. So for size in sizes. And let's create here arrays based on these sizes. np.random.random. We are going to create random arrays ranging between 0 and 1, and the size is going to be size. And first of all, let's perform our vector operation. So I'm going to find the sum of all of the numbers present inside this array using numpy sum function, which is a vector function. Let's start our timer here and let's calculate our sum of all the numbers inside this array. np.sum, and let's pass our array here. Let's stop the timer and again let's calculate the time difference. Paste this line right here. And we need to store this time so that we could later visualize it against our sizes. So let's create here two further empty lists. One is going to save the time of numpy functions and the other is going to save the time of our for loop. For loop is equals to empty list. And now let's append this time to numpy list because we are using here this numpy function. So numpy dot append, calculate time. Now let's do the same process using the for loop. For loop, and let's start our timer. Let's calculate the result, but this time we are going to use the for loop. So for I in array, we are going to iterate on each and every item of this array and we'll calculate the sum. So I'm going to save the result in this result variable, but it's going to be result plus equals array I. We are going to extract each element of this array and then add it to the previous result. So that's why I'm writing here result plus equals this thing. So it's going to be results. Actually, I have used here this results variable. So I need to put this results variable to 0. Results is equals to 0. Finally, let's stop our clock. Let's calculate the difference. And this time I'm going to append this time to for loop array. So for loop dot append calculated time. Now we have sizes and against each size we have the time for numpy as well as for loop. And it's time to visualize them. So let's import matplotlib, pyplot as plt, and outside this for loop plt dot plot, and along x-axis we are going to have our sizes and along y-axis we are going to have the time sizes, and we are going to plot numpy values. So just pass here numpy, and then we are going to plot for loop values. So again along x-axis sizes and then for loop, and let's put labels. So the x label is going to be sizes because we have used sizes, and y label is going to be time. And that's how you draw the time complexity graph. And yes, let's use a legend for each line. First of all, we have numpy plot. So legend for this line is going to be numpy. And then we have for loop plot. So legend is going to be for loop. Let's run it. Oops, it's going to be I here. And yes, we got our time complexity graph. But I think it's not that much informative. So if I take the semi-log of x-axis, then I am going to get a lot more information. So yes, let's take the semi-log x, and yes, semi-log x for the second plot. And now let's plot it. Now it's very informative. So when the sizes starts increasing from 10 to power 5, the for loop started taking a lot more time as compared to the numpy. So from this number onwards, for loop is taking a lot more time as compared to numpy. And that's why in the beginning I have told you that vectorization is an efficient way of computations. So I hope with the help of these three examples, you have understood how vectorization can make computations faster. And in the next tutorial, we are going to learn another important concept, and I'll see you there. Bye bye.